Alright, so for looking at adjusted R squared and our multiple regression, that sort of thing, let's take a look at some data that's based on a Minitab. Minitab is a statistical software. A Minitab tutorial I happened to land on at some point, and they were looking at presidents, and this H is their highest approval rating. So we see as low as 66 for a high and as high as 90 for a high. And then, and these just came off of Wikipedia actually. They seem to match what Minitab has. And then the R here, so that was the highest approval rating, and then for that same president, how historians happen to rank them. Okay, so ranking low is good. So a high approval rating is good, and a low rank is good because that'd be like first, second, third, that kind of thing. So whoever this was at number 2, high approval rating, very low rank, that looks really good. But we see that here's somebody with a 90 approval rating, 90% approval, and but only ranked by the historians as the 33rd best president. And so Minitab, they were just kind of looking at do these things have anything to do with each other, and fitting a model. And the first thing we can see, let's move my face more out of the way here, and as we look at what we see here, this certainly doesn't look like a straight line. Now it's not, in some ways, not too bad if we got rid of these 2 data points, and then we kind of see a trend that we might expect, in that, again, the higher the approval rating along the x-axis, the lower the rank, or the better the rank, which is a low number. And so these 2 kind of screw everything else up, but we can go into Desmos, and I've put a bunch of this stuff in, so we'll just kind of go through it a little at a time. So as you count here, there are 13 lines, and so my n is 13, so I just typed that in. I typed n equals 13 after I pasted the data in here. And notice I changed these, and all you have to do to change them is go up there, highlight it. If I wanted to call it J all of a sudden I could. So I just called it H, and got those data points in. There are 13 lines, so I have n equals 13 because I use n down here. Then to get Desmos to do a linear regression of just a straight line, you just need to tell it the parameters and so forth. So I said R, okay, again R, uppercase R, case matters. I used an uppercase R up here for rank. And then you use this tilde. Okay, that's typically way over on the left, up in the top above a opening quote, single quote, left of the 1, a tilde or a twiddles if you happen to be from Great Britain. And then my parameter, A1, okay, I called it A1 for a coefficient. And I put the subscript 1 on it, because this is a first degree polynomial, so you'll see that in a moment, but times h and then plus y-intercept b, and if I click there, it shows it, and there's the best fitting straight line. It gives me an r squared value. You can ask it to plot the residuals, which is just these deviations, and you could look at those. I'm not going to do that at this point. You can experiment with that. and it tells us the parameters. So we get our we get a negative slope, which is what I would expect, right? The higher the approval rating, the lower the number on the rank. And B at 32 is sort of meaningless. I mean, it's the average. Well, no, it's not the average, I guess, but it has to do with the average anyway of the y value or the r values there. So so I can get that, and then here what I do is I'm calculating the adjusted r squared. Now here's an interesting situation. Notice how low this r squared is, right? It's 0.028, so about 3%. So, and as you look at the data, yeah, these data are far flung from this line. This straight line only accounts for about 3% of the total variation in there. And so when we do our blowing up of the unexplained part by n over n minus 1 over n minus 1 minus 1. So n is 13, so I'm taking 12 divided by 11, and this number, the 0.028 or about 3%, is so small that it actually causes my adjusted r squared to be minus 0.06. Now probably what you would report is 0, an adjusted r squared of 0, not a negative number, but because technically it really can't be negative, as far as it explains less than nothing. I don't think so. So 0 would be probably what you would report, but it shows here that the adjusted r squared is really low. Well, of course, the r squared is really low. And so now we move on to, what about a quadratic? And so I do the same thing, r tilde. Now I have a2h squared plus a1h plus b, so I'm saying desmos, fit this model. And as soon as I use that tilde, it's expecting to do this, so it did it on its own. And again, I get an r squared, way up to 40%. And let's put that in there. And so there's my quadratic. Yeah, I guess it looks better than the straight line, right? Because the straight line certainly didn't seem to take into account this stuff up here, but the quadratic is taking that into account, and then I compute my adjusted r squared again. Now I haven't figured out if I can get at that r squared number very easily. I'm pretty sure I could if I was programming it in JavaScript or something, but here this way I don't know. I don't know if there's any way to get it other than I just typed it in. So again, what I did was I took 1 minus the r squared and then multiplied that by my factor of n minus 1 over n minus k minus 1, and you see I'm using h and h squared, so 2 columns, so I've got n minus 2 minus 1. Up here I had n minus 1 because I just had the h column, and so I do that and I get my adjusted r squared of 0.2766. So r squared says this model explained about 40%. If I make it the adjusted r squared, where I penalize using more columns, you see, well, it's not as high as the 39.7% or 40%, but it's not doing bad. It's almost 28%. It's still at, or 0.28, and way better than the straight line. So I kind of like this quadratic. So let me get rid of that by turning it off. Now we go to a cubic. And with the cubic, Wow, see, that's starting to look pretty darn good, as far as fitting the data. Now, this is all just silly. I don't know what a cubic model would mean for such data. Okay, the point here is we're just trying to look at this use of adjusted R squared and R squared and so forth. So here we fit the cubic. We get an R squared of 0.59, so almost 60%, so that's looking good. We've got our coefficients here if I wanted to make the graph of that thing myself. And then I do my adjusted R squared. You see I take my 1 minus the R squared, the 0.5929, multiply by the n minus 1, and then divide by n minus 3 minus 1, because I've got now 3 columns. And I look at that and I see I get 0.45. That's better than the 0.27. So that looks good, and I'm going to keep going and just to kind of see what happens. But see, that's looking pretty good. So I'm going to get rid of the quadratic, keep the cubic. Now let's look at a quartic, a fourth degree polynomial. It's also blue, but that's that one. And I guess I would say that maybe seems to fit the data better just eyeballing it there. It's got that funny little lump in it, but not bad. And it's interesting. You could say, well, yeah, it's sort of a it follows that negative direction that I would expect until you get to some really high approval ratings. Then all of a sudden maybe they jump up, and this could actually make sense. Is that how do you get the high approval ratings? Oh, probably you did something in war that people got behind, and so they thought you were really great. Think about things like World War II, Armistice Day and things like that. That, oh wow, hey, we must have made the right decision, and so you maybe have great approval for the president, or reaction to things like 9/11. The president reacts, and we're all behind the president. We say, oh yeah, that's great, and so those could cause you to have very high approval ratings as your highest approval rating. But overall, maybe you got us into a world war, and you shouldn't have. Maybe if you had been a better president, you wouldn't have gotten us into a world war or something like that. Who knows? But at any rate, it's possible that could explain it, right? And all of a sudden, the model is helping me think about something like that. Don't know if that's true. Again, on the whole, this is just sort of silly data in a way. But it helps us see this whole idea of adjusted R squared. So there's my fourth degree polynomial. We get an R squared of 67. Here it was 59%. Now we're at 67%. And again, the adjusted R squared went up a little bit. It went from 0.457 to 0.511. So yeah, okay, that looks good. We go with a fourth degree polynomial. So let's turn off the cubic and try a fifth degree polynomial. Now notice what happens here is they almost look alike. Okay, not exactly. They're a little bit different, but they are really close. And now because of that, notice the R squared values. The R squared did go up 0.6744 from 0.6743, but they didn't change much. But now we get to see what that adjusted R squared does. These are about the same R squared value, but notice that because of the putting in the 5 instead of the 4 with the 5 parameters, all of a sudden that adjusted R squared drops dramatically. And so it's looking to me like probably the fourth degree polynomial is the thing to go with in this case. Okay, I have no reason to guess any other particular model. and so if I'm just looking at this fourth degree polynomial and keep adding columns based on powers of h, it looks to me like, hey, this is it. My adjusted R squared peaked at 0.511. Looks like it's going down now at 0.44. Let's take a look at, I've got a sixth degree polynomial in here. Notice it starts to actually look kind of worse. However, it doesn't. Notice the R squared still went up. Typically, as you add columns, the R squared will go up. And that's, again, a reason why you want to use adjusted R squared. So it went up a bit, not a lot, but went up to almost 70%. But notice the adjusted R squared dropped even further down here to back down to about 0.395 or about 40%. So the adjusted R squared for the I've got that written as A5. Notice I better fix that. 6. A6. Then that adjusted R squared for the sixth degree polynomial is about the same as... Oh, no, I was remembering the R squared, not the adjusted R squared. I was thinking it was the same as the quadratic, but, well, it's the adjusted R squared is about the same as the quadratic's R squared. So, no, they aren't the same. But its adjusted R squared is worse than the cubic's adjusted R squared. Okay, so going to a sixth degree polynomial, it made R squared better. Not lots better, but better. But it made our adjusted R squared much worse. So probably, in this case, our winner is our fourth degree polynomial with an adjusted R squared of about 0.51. Okay, and that is the idea of using adjusted R squared and multiple regression, because that's what this was doing. Every time I added a column, it was just doing a multiple regression with more columns. So here we just had an h column, then an h squared and an h column, then an h cubed, an h squared and an h column, h to the fourth, and so on. So we just kept adding columns. We got better and better fits. Our R squared showed that. But we peaked in our adjusted R squared at a 4 here with the fourth degree polynomial, and then things started dropping like a rock. Okay, and so probably on that sort of criteria, we should go with maybe the fourth degree polynomial to fit these data as not being an overfit, but at the same time fitting the data pretty well. We got clear up to, for our R squared, up to 67%. That's not bad. And again, it was the highest adjusted R squared. Okay, so we're going to go with that model for these particular data. All right, and that is one look at an example using adjusted R squared to fit some data, in this case to a fourth degree polynomial.